Now let's try to understand multiplication. How to design circuits for multiplication. To understand that, first of all you should understand how you do multiplication using paper and pen. Okay, so well, let's try that. So example, let's say you have two numbers 1011, 1101. I am assuming that let's say these two are first unsigned numbers. After that I will extend this concept to signed numbers, right? Two's complementation. I mean, did you remember the two's complement representation? We will come to that point later. At this moment these two are unsigned numbers. If it is an unsigned number, what is the value of this binary number? It would be 2 power 0, 2 power 1, 2 square, 2 cube, 8 plus 2, 10, 10 plus 1, 11. This is 11 and this is 13, right? So 11 into 13, it would be 143. So we should get 143 as the answer for that, whether it is correct or not. I mean, we'll try this method. 1.1, 1. 1.1, 1. This is multiplication. 1.0, 0. Just usual multiplication. You know that, right? 1.1, 1. In that way, I am multiplying 1011 with the first bit of multiplier. So this is called multiplier. This is called multiplicand. You know that, right? Now this time I take second bit of multiplier and I multiply the multiplicand. Whenever it is 0, 0.10, 0.10, 0.00, 0.10. In that way, second row will be created. These are all called partial sums, right? Now we will go to the third bit 1. With 1 we multiply 1011 again. Now we understood that we are going to get 1011, right? Now next time if I multiply with this one, we are going to get again 1011. This is a usual multiplication. Let us check whether it works for binary. Generally for decimal it works. So number systems are having very good reasonable logic. I mean, otherwise I can say all the base systems are compatible. That means if you can do multiplication using decimal, like using base 10, the same concept we can apply for binary, hexadecimal, everything. So that multiplication model works. So 1, 1, see 1 here, 1 plus 1 plus 1, 3, right? So if since it is 3, so 3 means what? 1, 1. That means this 1 is here and this 1 is carry. So 1 plus 1, 0. Then here 1. 1 plus 1, 0. Then here 1. 1 plus 1, 0. Then 1 will be carry. 1 plus anything, some 0 is 1 now. So this will be the answer, right? So if I simplify, I mean if I convert it into decimal, what is going to happen? 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7. I would like to know the value. 128 plus here 8 plus 4 plus 2 plus 1. If I simplify, it would be 136, 140, 142, 143. Perfect. So using paper and pen, generally we solve problem like this, and that is exactly correct answer. That means it's working, right? So we try to implement this model, whatever I did. So exactly the same thing we are going to implement using circuits also. So I'm going to teach you three things. One is the basic model and very fast, which is array multiplier. Okay, but it takes lot of space. We will see that slowly. So first I start with array multiplier, which is directly taking this idea. Second one we will see sequential multiplier. So sequential multiplier. Then we see the optimized multiplier, which is Booth multiplier. Okay, so Booth multiplier is generally faster than this sequential multiplier. Okay, and it won't take much space like array multiplier. That details I will be clearly explaining, but I am just giving you the outline what I am going to teach you. Array multiplier, then I explain you sequential multiplier, then Booth multiplier. Okay, these three we will see. Sorry, so it is, this process is called array multiplication, this process is called sequential multiplication, and third one is Booth multiplication. All that we will see. So what I am going to do is I am going to do multiplication in a different way. So try to understand this way also. 1011 and 1101. So here you have partial products, right? So rather than adding them in the end, I will be adding whenever I create one partial product. That means I calculate the cumulative sum. We will see that 1 1 1. So 1 1 1, 1 0 0, 1 1 1. From now onwards, whenever a multiplier bit is 1, then multiplicand should be written. Next, so 0 1 0, 0 1 0, 0 1 0, 0 1. Whenever this bit is 0, always you get everything will be 0. Now immediately do the partial sum. You get 1, 1, 0, 1, 0. Then continue the process. Now third bit. So 1 again, since it is 1, we have to write 1, 0, 1, 1. But we know one thing, right? We have to start from where? From the third bit, right? 1, 2, 3. So here 1, 1, 0, 1. Again immediately do the partial sum. 1, 1, 1, 1 plus 1, 0, 1, 1. Then, so remember previous time we added here, next time we have to add here, okay, from here. So the bit is 1, then we have to start here 1, 1, 0, 1. So 1, 1, 1, 1, 1 plus 1, 0, then you get here 0, 1, 1 plus 1, 0, 1, 1 plus 1, 0, 1 here, right? So this would be the answer. 2 power 0, 2 power 1, 2 square, 2 cube. So this part if you see 15, this is 2 power 0, 1, 2, 3, 4, 5, 6, 7, 128. 128 plus 15 is 143. Already we have done here, right? So you can check it out. 000 followed by 4 ones. So what is the driving point here is, so this step if you understand, I am going to create a circuit which is exactly mimicking, otherwise which is going to simulate this model, okay? For that what I am going to do is, I will tell you. First of all, you tell me how to create 1011 which is multiplicand. Example, you have multiplicand, okay? So what is that? 1011. So now just I show you how to multiply using the circuits now. So far we have seen, we understood the idea, but now we are thinking about how to do this process using circuits, right? What kind of circuits are required here? I will tell you for that. Since the multiplier is 1, then we have to get answer 1011, correct? So you tell me what circuit can generate 1011 when I multiply with 1. Very simple. So actually 1.1 is 1, correct? This is nothing but result of this and this, AND gate of these two. Similarly, AND gate of these two, 1.0, 0, 1.1, 1. So I am showing how to create, this kind of result, just this part, okay? What you do is simply take your multiplicand. Let us say these values are M0, M1, M2, M3. Otherwise, let's use a name called A. A, not A1, A2, A3. This is your multiplicand A. I use M for multiplier. So this one, take one AND gate, connect one of the input to A3, remember it. Next, take another AND gate, slowly you will understand, don't worry. A2, take another AND gate, in that way take 4 AND gates, A1 and A0. Now here what you give is, you simply give 1, okay? That means this entire this input should be connected to one common variable. What is that? That is going to be a multiplier bit. So assume that that multiplier bit is M0. If I do it like this, then definitely we are going to get an output which is nothing but the first row, right? So always try to solve this problem using divide and conquer. That means whatever the subject it is, first understand smaller parts, then try to build a big thing. So always remember, every successful person will first of all will start with small things. After that he will make it big. Here also same thing. We are just understanding how to imitate the multiplication of one multiplicand versus one bit, correct? So let's try that whether it works or not. If M0 is 1, so what is going to happen? 1 will be passed to every AND gate. Now already A3 is having 1 here, 0 here, 1 here, 1 here. So 1.1, it creates 1 here, it creates C. So what is A1? 1. What is this one already? 1. 1.1? 1, right? So here you get 1. Then here it is 0.1, you get 0. Then here, this is 1 again, 1.1, 1. So what if I give M0 as 0? What is going to happen? So definitely 0.1, 0. 0.10, everything should be 0. Yes, obviously one of the input of AND gate is 0, then we are going to get output as 0. So it's perfect. Now finally I understood how to create a circuit for one level of multiplication, otherwise one multiplication. right? We will be repeating this process. Then we will be repeating the circuit. That is what I am going to do. Now whatever the concept I am teaching you, that is actually array multiplier. Okay, so you understood this point, correct? But remember one thing, we need something extra. Are we simply doing, just multiplication? No, we are applying the multiplication with every digit. Then we are also adding two partial products, correct? So how to do that part we will see. Okay, at this moment I show this part, how to add one, partial product to another partial product. Example, this is partial product 1, this is partial product 2. How to add them? Okay, we will see. So how to first generate this partial product? Same thing, correct? How you generated this partial product? In the same way. For that you need another circuit. Let me construct here. Okay, so here again you require 1 2 3 4 gates, right? And remember one thing, all that, see, 0 0 0 0 is because of again your multiplicand and second bit, correct? So here a3 a2 a1 a0 are again fixed, a3 a2 a1 a0, remember it. Okay, I'll clearly show here. Second level we are doing, but remember one thing. So why I want to move my circuit to this side, I will tell you spatially. First blindly see the procedure what I am doing, a3 a2 a1 a0. There is another input. This input has to be, taken from where? Second input, because we are multiplying, otherwise we are getting this result because of second multiplier bit, right? So all the circuits to be connected to second multiplier, remember it. Okay, second multiplier. So here it is a0. So multiplier, for multiplier we'll give some names, right? This is m0, let's use m1. So now again a0 a1 a2 a3, here a0 a1 a2 a3, but the bit here is m1, here the bit is m0. Once you get these two results, what are we going to do? We are going to do addition. That means we need adder circuit. We have to add what and what? These two, right? We have to add these two. We have to add these two. That's it, right? For that, what to do? How to neatly fix the full adder circuit? We will see. We need a full adder actually here. I will show that. Okay. Now see here. So I am taking again multiplication 1 0 1 1 versus 1 1 1 1. So I am showing only two partial sums, I mean two rows. One is 1 0 1 1, second one also 1 0 1 1. So what are you going to do? Already I told you we have to add them, right? 1 plus here actually imagine one dummy 0. So unreal 0. 1 plus 0 1. Then we are adding these two, right? So 1 plus 1 0, you get here 1. 1 plus 1 0, you get here 1. 1 plus 1 0, you get here 1. Then you have to add these two, you get 0 here, sum, and carry should be propagated to the next level. That is what we need. Such a circuit I want. Now so I am showing with example circuit. We constructed this already, right? a0 a1 a2 a3. This is a0, this is a1, this is a2, this is a3. This is your m0, this is your m1. So here I am going to give input m0. Okay, example m0 here 1, I am going to give 1, depends on that. Okay, m0 is a variable. So don't worry how this m0, m1, m2 will be generated. Okay, that's a separate story. It's not very difficult to understand. Assume that let's say m0 contains a value, maybe 0 or 1, whatever, that will be propagated. So here we will be getting m0 dot a0. So exactly here, example, if it is 1 and this is really 1 0 1 1, then you are going to get here 1 0 1 1 because of the AND gate, right? AND gate's result I am writing here 1 0 1 1. Now what do you want to do again? Here m1 is 1. Then if this circuit is implemented, so a3 a2 a1 a0 again 1 0 1 1, then these AND gates are going to produce again 1 0 1 1. So what is the next step you want to do? You want to add them, right? So like this. That means these two AND gates you want to add, these two AND gates you want to add, these two and this one. I mean whatever the carry you get, with that you want to add this one, correct? So I want lot of adders here. Okay, we will see that. So definitely we need adders, we will do. Once you design example, what I do is here I create one full adder. Otherwise I have one full adder here. Here I am going to construct full adder. Let's show with circle like this. Because why Mr. Example, this AND gate name is something X. My dear X, why do you want full adder? Because there is one more AND here, that's result and this result should be added, right? That's why here you require full adder. Similarly, this and result should be added, correct? So we require full adder. So why full adder, sir? Why not half adder? See here, because sometimes what happens, so when you add these two, you are going to get sum, and carry will be propagated to the next level. In the next level there will be 3 digits. That's why I have to have full adder sometimes, right? That's why for simplicity I am assuming that everywhere I am fixing full adders. Okay, so here definitely you read full adder sometimes, correct? Why? Because this full adder has to add this and result and this and result plus this carry of this full adder, correct? That means this full adder is going to generate a carry, that also to be added, right? I am just explaining the requirement. So how to construct such circuit? It looks very big, right? Yes, definitely. Here also we need full adder. Assume that we have full adders here, that full adders are going to do the appropriate thing. Okay, so this full adder is going to add these two, this full adder is going to add these two, this full adder is going to add these two, plus of course carry, this full adder also adding these two and carry, in that way. Now after that what you are going to do, next level, right? M2. So we will be multiplying this 1 with 1011. What you get again? You get 1011. We will be adding 1011 from where? Recall. This is partial sum. Because of this full adders, see how many full adders you require? One here, one here, one here, right? And one here, 4 full adders. So 1, 2, see here, 1, 2, 3, 4, right? So what I want to tell you is that full adders, whatever the partial sum they create here, I can say some partial sum is created because of the circuitry, right? So that partial sum should be added to next again 1111. 1011, correct? So I show here. The next level when you multiply, you will be multiplying from here. The first time here, second time we start here, third time we start here. 1, 1, 0, 1. Okay. So now if you see, this 1011 is created by this AND gates. But the only thing is this 1011 should be added to this 00001. Okay. So this C is going to be 1. This full adder is going to create 0 sum. This full adder is going to create 0 sum. This full adder is going to create 0 sum. This full adder is going to create 0 sum, in that way. Okay, such a circuit we want. I am just giving the rough idea. So by this time you should have idea. Every time here also to add this sum and this sum, we need again full adders here. We will take the help of one more set of full adders. So here, how many full adders required, we will see that details later. Maybe sometimes I may not write exact full adders, but understand the concept. So why these full adders? Again to add here and here and here and here in that way, here, correct? So again you need some set of full adders. What I realized is in the every level, apart from the first level, in the every level you need AND gates to get the product. Second thing, you need full adder to add current row versus previous cumulative sum, right? So now finally I got a full realization that in my circuit which I am going to realize, I need full adders in every row almost and AND gates in every row. Let me create that as a package. I will show you example. So I am repeating the circuitry, correct or not? I will show that circuitry. So this AND gate and full adder one package, AND gate full adder, in that way the combinations are repeated, right? Are we having complete heterogeneous circuit? No, we are having completely repetitive circuit, otherwise same circuit everywhere, right? So see here, and that means you need some set of AND gates, and every AND should be associated with some full adder, right? So in that way, so we will be creating array multiplier. Now I will show exact implementation. So far you just got idea how that array multiplier looks like, what kind of components it will have, because it will be little bit difficult circuitry. That means it's a lengthy circuit and it has a lot of gates and all. So directly if I take my array multiplier and if I explain, you don't understand anything. That's why I am just giving you foundation what we are going to do. Okay, so in this process sometimes it will be boring, and sometimes what happens, so you will be thinking that we are doing what, but end of the day you will understand everything. So why I am doing all these things. Okay, now let me clear what I did finally. Just I explained you the multiplication process in a different way. What is that? Every time I am multiplying with one digit, then whatever the result I get, I am adding that result to the previous sum. That is what the way we are multiplying. The same concept I am implementing using the circuits. Now we will see the final circuit design, which is nothing but array multiplier. Okay. So finally we are going to create a small devices. Okay, and we will be repeating the devices everywhere because we want same kind of work everywhere, right? Addition and product. We want product here, see, everywhere. So we want 1.1, 1.0, 1.1, 1.1. We need just product every time, correct? After that, addition, 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 addition. You will be adding, adding, adding. So you need everywhere one product, one addition, correct? That's why. So we will be having this kind of circuit first. First understand this circuit and I will show the place of this circuit, what the circuit is going to do. First of all, this is your bit in your multiplicand. Okay, this is one of the bit in multiplicand, AJ. Now MI is a bit which is nothing but one of the multiplier bit, multiplier. Now this is carry in. So here you see, when you are adding, see, we will be adding first of all. Okay, so already I told you, when you add, then you get a carry, right? Example, when you add these two, if you get a carry, that carry should be propagated to next level, right? So similarly, so I mean here you see, for these two bits when you are adding, before that, so one carry will propagate to here, then that and these two bits we will be adding, right? In that way, everywhere, every line, so need one addition, but that addition is not only 2 bits, one carry also might come. Of course here there is no carry, but sometimes you get, isn't it? You should be prepared for that. So that is what we are going to do in this component. So I will be having one full adder because I am going to get one carry from the previous computation. So that is carry in. Now once you get full adder, before that, why this AND gate? Recall. So we will be multiplying, using one multiplier bit and one multiplicand bit, correct? Everywhere you see 1.1, 1.1. To do that we need AND gate, right? This AND gate. So what is this AND gate is now currently doing is mi.aj. So this is going to develop mi.aj once. So what is this blue line? Bit of incoming partial product. So once you generate this kind of, here I show this kind of bit using AND gate. So what are you going to do? We are going to add one more bit which is going to come from previous level of partial sum. So one bit is going to come from the next from the previous level. So that I will be taking, I will show how to take it. Okay. So now this one and example, this one is this one. Now what is this one? Just now I got this product, right? This one because of this AND gate. Now we have to add. Sir, only these two? No. One carry comes from here, right? Previous level. So that is carry in. That's why this carry in bit, this AND gate result, that means the output of this AND gate, and one bit will come from the next level. So that all these 3 bits I add. When I do addition, then I will get sum, right? So thus sum is going to be the again partial sum bit. So this sum is going to next level, right? If you have another addition, example here you see this partial sum bit is added to this, right? Then you are generating one more partial sum bit. So this will be added to the next level, right? So that is what going to happen. So that is about this sum. Next, anything else? So we understood what is carry in, we understood multiplier bit, multiplicand bit, they will be ANDed. After that, one incoming bit will come and this one we have to add. Then you get sum and carry. Sir, what about the carry of this? You did not teach. Yes. So this full adder is going to get going to have a carry. That carry we will be sending to the next level. Okay. So here we will be having this kind of circuit here. That is going to generate a carry to the next level. Okay. So there will be one more this kind of circuit here also. Multiple circuits we will be creating. So these circuits carry we will be giving as a carry into the next circuit. That's it. Like we got a carry in from right side, right? In the same way, this carry is going to right side. That's it. So all these things I explained. Now I will try to connect this circuit to this problem. Okay. So let me show that. Example here 1011 1111. You know the calculations. It is A0, A1, A2, A3, M0, M1, M2, M3. So first of all, let's have some calculation. 1, 1 0 1, and after that 1 1 1 0, you know that, right? So you get 1 0 1 1 two times because everything is 1. Now after that you do partial sum. So here I am not showing you how the circuit is going to do all this stuff first. So first what I do is I just allow partial sums first. 1 1 plus 1 0, 1 plus 1 0. I am not explaining the any computation here, don't try to understand. So finally let's say this calculation is done by your circuit. Now what are you going to do next step, you tell me? Already you applied m0 into this one, or done, m1 into this one, done. After that partial product you got. Once you get partial product, then we will be doing what again? We are going to take the third bit. Now this moment I will be taking m2, which is 1. Then m2 will be multiplied with each and every digit of your multiplicand, right? Then what are you going to get here? First 1.11, then 1.11, then 0 1. Okay, this part also I don't want to explain now. So I would like to focus on the area where I can show the relevance of this one. Slowly we'll understand. Example here. Okay, so here I show. First thing, what are the things you are doing here? I will show. So this is incoming bit, right, which is coming from the previous partial product. Okay, remember it. Apart from that, how did you get this bit? This bit you got because of m2 dot. So I can say that this bit is nothing but m2 dot a3, right? Remember. So 1 is nothing but m2 dot a3. Once you get it, then what are you going to do? Just we are adding these two. To add, so you need carry also, right? This carry is going to come, right? So this carry, whatever the, because of these two sum, you are going to get carry. That carry, this bit we are adding, right? Assume that that bit is something x. Then we will be adding x plus m2 dot a3 plus this carry in, right? Carry in. Now see the circuit here also, carry in plus this is mi dot aj, like m2 dot a3 plus some bit of incoming partial product. This is bit of incoming partial product. These three will be added. So once you do that, you will be getting again sum and carry. Carry will go to right side, okay, or left side, whatever, this side. Then sum will come down side. So that in the next level there will be another this kind of circuit. For that I am going to connect. Okay. So now this kind of circuit we will be repeating and we will be realizing, otherwise we are implementing multiplier circuit. We are going to do all this stuff using this. Okay. So clearly see what are the things we have. One AND gate, one full adder, right? So remember that things. So now I am going to construct complete multiplier circuit using this building blocks. Okay, this building block is important. Focus on that. Right. Now we'll see the complete circuit. So far we have seen basic building block, right? This one. So this will be repeated everywhere. Okay. So the remaining circuits, if you see, I will slowly explain them. Remaining functionality or cables, everything. First, we try to understand what we are going to do. I'm going to just explain you, otherwise I'm going to simulate this multiplication 111 into 111 using the circuit. So while doing that, we understand how this each and every gate is working and each and every circuit is going to do, right? Let's do that. This is actually 7 into 7, 49. I'm assuming that these two are unsigned numbers, then it is 49 actually. Okay, 32 plus 16, 48 plus 1. Now I explain the process how I am doing this one. Initially, I assume that I have a partial product called 0, 0, 0. Then immediately I take the first multiplication, otherwise first row of the multiplication. That means I multiply this 111 with 1. So 1.1, 1, 1, 1. Once you do that, automatically we have to do addition, right? So we will be doing addition. So 0 plus 1, 1, 0 plus 1, 1, 0 plus 1, 1. So this is the partial product 2. Let's say this is partial product 1. This is partial product 2. So this partial product 2, once we get, then again we are going to do multiplication. We take second bit, again you multiply. See 1.1. We know the process, right? Then you add these two. 111. This 111 should be added. Okay. When you do that, you get 1 here, 1 plus 1 0 here, then 1 comes here. 1 plus 1 plus 1 1, then 1 is the carry, 1 plus 1 0, then 1 is the carry, 1 will be here. So this is a partial product 3. So remember one thing, if you multiply 111 with 1 1, you are going to get this answer. because 7 in 3 is a 21. This is actually 21. 16 plus 4 plus 1. Once you have this partial product, then you take 1 and multiply this 1 with 1 1 1. You get here, see, 1 1 1. Remember one thing, first time see the positions of 1 1 1. Second time 1 1 1 here. Every time we have to do left shift, right? So that is one thing you should remember, 1 1 1. So 1 here, 0 here, 1 plus 1, that is a process, you understand completely. Now we are going to get the final partial product, which is final product PP4, 1 1 0 0 0 1. Okay, so first I will show you where is this 0 0 0 computation. That is, initially your circuit, which is nothing but your full adder, is going to take 0 0 0 as the first input. Full adder will have three inputs, right? One is coming from this partial product, second one is carry, third one is AND. Here also carry, this partial product, one of the bit in partial product, and AND gate. Everywhere same thing. Okay. Now, sir, what is this 1 1 1? This is nothing but multiplicand. Okay. So this multiplicand can be written like this: A2, A1, A0. I am assuming it is as A0, A1, A2. So I will show here. See, A0, A1, A2. This A0, A1, A2 is multiplied 3 times, right? That means we have to multiply A0, A1, A2 with M0. Let's assume that this 1 1 1 as M0. This is M1, this is M2, right? In the first step, we are multiplying A2, A1, A0 with M0, second time with M1, third time with M2, right? So for that, to facilitate that, we will be doing like this. See, A0, first time M0, A0 will be multiplied here. See, M0 dot A0, right? Similarly, just tell me what is the procedure. A2, A1, A0. In the first row, what should happen for first multiplication? M0 should be multiplied with everything. Then you should get M0 A0, M0 A1, M0 A2, right? Sir, where are we getting these products? See here, M0 A0, this one. So this cable is M0. So that is supplied to all the blocks. So here we have M0, but this is A1, right? See, now similarly M0 A2. Second time, after some time, in the second row, we will be doing calculation, multiplication like this. What is that? M1 A2, M1 A1, M1 A0, right? Sir, where are we doing that? Please show that. See here, M1 A0, that M1 will be carried here. See, M1 and A1, M1 A1. Now here, see here, this is M1, this is A2, M1 A2. In that way, so we have this multiplications. In the next level, M2 here, M2, what is this one more input? See this one, what is that? This is coming like this, A0. So it is A0, it is A1, A2, right? So M2 A0. Here, this is M2 A1, M2 A2. So in that way, so that is the functionality of AND gate. You understand? Now we'll see the complete story. What is going to happen? Focus on the first row first. What is going to happen in the first row? We will see. When you give signals like this, A0, 0, A1, 0, A2, 0, initially, and M0 everything, first this AND gate starts working, and everything, like all the circuit will start working here, all the circuit. So because of that, what is going to happen, we'll see. So this 0 0 0 is nothing but this 0 0 0. Fine. Second step. So M0 A0. Similarly, M0 A1, M0 A2. That means multiplication process. This process is done here. So when really if you do that, this is here in this problem, it is 1. 1 dot 1 1 1. What you get? 1 1 1, right? So that is you are getting here, you see. M0, let me take 1. So this is A0 is 1, right? Okay. So 1 dot 1, 1. AND gate is giving you 1 as output. Now this AND gate is going to give output 1. Let me show here. So 1 1 1. Finally we got 1 1 1. Now what is the next step? Once you get 1 1 1, we should add 0 0 0. That's why you see 0 0 0 are added, you see. 0 and 1. 0 and 1 are added. Sir, what about this? Full adder generally takes 3 inputs, right? At this moment it is not relevant. That's why we give 0 input. Another input is just dummy. We give 0. 0 is just for completeness. Full adder has to take 3 inputs, but actually we have to give only 2 inputs. That's why another pin will be connected to 0. 0 plus 1 plus 1. This is done here in this full adder. So what is the result you get? 1, right? So that is output, directly answer, you see. This 0 plus 1, 1 is directly answer, remember, okay? Now, sir, what is this full adder's output? Simple. 1 here. So this, what is the carry of this full adder? 0 plus 1, 1. No carry, right? So 0 plus 1, no carry. Then 0 will be carry here. So now 0 plus 1 plus 0. So this process is going on here. So you get again 1 here. Remember it. The sum of this full adder. Next, sir, what is the carry? No carry. So 0 will propagate like this. Now, sir, what happens here? That 0, this 0, and this one is nothing but this one, and one more input, carry, which is 0. These three will be added, so you get a sum called 1. Okay, fine. Sir, any carry? No carry, right? So again, same story. 0 plus 1 is 1, so no carry. So carry 0 will be propagated. Now, if you see the final answer, so here 0, 0, 0 plus 1, 1, 1 is 1, 1, 1. You can see here 1 and 1 and 1. Perfect. Now next step. In the next step, what happens? This 1 will go down. This 1 will come to this block. This 1 comes here. This 1 0 comes here. Okay. Remember it. Now in this step, what is going to happen is, again this AND gates will develop products M1 A0. Okay. So we know that M1 is 1 in our problem, and A0 A1 A2, for simplicity we took 1, right? So 1 1 1. Let us apply multiplication here. M1 A0. You get 1 here. You get 1 here. You get 1 here. Sir, what is this 1 1 1 significance? This one. Now see the spatial positions also, right? See here 1 1 1 is exactly under this 1 1. See, this one is important. Let me erase unnecessary things here. Okay. Now what is important for me is this sum of the full adder 1 1 1. Correct. So this 1 1 is this 1 1. This 1 1 1, right? 1 1 1. That 1 1 1 should be added to 1 1 1. That's why 1 1 1 will be added to, see, 1 1 1. Correct. So this 1 should not be added to this one. This 1 should not be added to this one. That's why this is the arrangement, right? Now here what is going to happen is, this 1 is going to come here. That is what we want. 1 1 will be added. Similarly here, this 1 and this 1 will be added like this. This 1 and this 1 will be added. So whatever the carry comes, that will go to the next level. Yes, whatever the carry comes here, that should go to the next level. That is what, we built. Okay, we'll just try it out. What happens, we will see. So finally in the next level, what is going to happen is 1 plus 1. So this block will work first. So 1 plus 1, because it has all the sufficient information. So 1 is coming from here. So this 1.1 is 1, right? 1 plus 1, full adder. 1 plus 1 plus 0. You get 1 here. Okay, fine. Next. So these full adders carry, because 1 plus 1 plus, So here there is a mistake. 1 plus 1 is 0, right? What is the carry? Carry is 1. Then carry comes here. Now let me focus here. 1 is coming from here. This AND gates result 1, and this carry is result is 1. 1 plus 1 plus 1. What is the sum then? 1. This sum is 1. Okay. So what is the carry? 1 here. Okay. Now see here. This is 1. This is 1. Anything else? See, this one 0. So this full adder's carry is connected here. Okay. Then what happens? 0 plus 1 plus 1. 0 is the sum. Carry 1. So that carry will be, going like this to the next level. That is what generally happens, right? When you add the things, when you get carry, it should go to the next level, right? That is what happening here. Now just focus on the next partial sum. First partial sum was 1 1 1, right? Here 1 1 1. Next partial sum should be 1 0 1 0 1. Is that true? We will see. Next partial sum, if you see, so here start. So the next partial sum 1, see here 1 0. I show from here. Just mark this one. 1 0 1 0. Yeah, 1 1 0 1 0 1. For that 1 0 1 0 1, we have to add again triple 1. So here we are adding triple 1. See 1 1 1. This is triple 1. Okay. So this you can understand slowly that what is going to happen. Now I already explained this one. Now I have to explain this box. So what is the result of this box? This full adder is going to give 1, right? This AND is 1. 1 plus 1 0. Sum is 0. So carry will propagate like this. Remember it. Okay. Now come to this box. This box, how you do the calculation? First of all, AND will be done. So we know that the result of AND is already 1, right? So full adder is giving what? 0, right? 0. This 0 plus 1. Now what is the carry? We should know the carry. I have forgotten to tell you. 1 plus 1 0, then carry is 1, right? So here there is a carry. 1 plus 1 is 0, then here carry is 1, right? Now come to this box. Now can I say one thing? This box calculation is depending on this box and this box. This box carry is connected to full adder. This box carry also connected to full adder, correct? That's why we should be careful. Then what happens? 1 plus 1 plus 1. 1 plus 1 plus 1, 1 as a sum. And what is the carry? Carry is 1 again, correct? Remember, 1 plus 1 plus 1. So sum is 1, carry is 1. So finally, this will be the final carry. Now you see this one. So now answer is 110001. So you check here 1 1 0 1 1 0, then 0, yes 0, then so 1 1 double 0 1 1 double 0, then 0 1, see 0 1. So let me mark them. This is first bit. I can say in the result, let me show result as like this: P naught, this is P1 and this is P2, right? This is P3, this is P4, and the final carry is nothing but the P5 bit, this one, okay? So this is about array multiplier, which is here multiplying two 3-bit numbers, okay? So 1 2 3 4 5 6 7 8 9, you need 9 blocks. Each block contains one full adder and one AND gate. So these are the details about gates. Now in the exam, what they can ask is, so one time they asked what is the time complexity of multiplication, okay? So what is the time complexity, we will see. For that, time complexity is nothing but they asked with respect to number of gate delays, okay? So how many gate delays are there approximately? So they asked in asymptotic notation. That means they did not ask exact answer, but they want to have, you know, a rough idea. That means asymptotic idea. Example, when you are multiplying to n-bit numbers, okay, n-bit numbers, then we should get result here, right? I mean, immediately you get result here, and this calculation will be done next level. In the next level, this calculation will be done. After that, this calculation. After that, this calculation. Ultimately, to get the final bit P5, this box should work. But this box is depending on this box and this box. And this box is depending on this sum and, you know, this one, right? Because so carry should come from here and sum should come from here, right? So similarly, this box is depending on, because this box full adder is connected to this full adder, and you know, one is carry, of course 0, but one more thing, anything else? No, only these two, right? Carry is of course 0, but it is depending on this one. But this box is depending on, so this full adder is depending on this full adder's carry. So it depends on this one. This box is depending on, so this sum, right? So this full adder's one of the input is connected to this full adder. So this full adder is depending on this full adder because carry is coming from here. So finally I can say that the delay depends on the maximum path length, correct? See, your signal should go like this. So your full adder should give the result, that should be taken here. This full adder sum, you know, should come here. Of course, that full adder's carry should come here. Then this full adder should work. So without this full adder, it can't work, right? Because these two are connected. Then signal should come like this, then like this. So easily we can understand that. So the delay is, see, let me count it. 1. I'm just checking how many this box is depending on this box. This box is depending on, of course, this box and this box. Then you see 1, 2, 3, 4, 5, 6. So at least, you know, 6 gate delays are there, correct? 6 gate delays are more than that, correct? Otherwise, this entire box has delay x, okay, whatever it is, x delay. This entire box is creating one unit of delay, x delay. Then how many such x delays we have? X generally represents variable, right? For easy understanding, let's assume that this box is having some delay called constant delay c. Now we'll see the delay. So here this box is connected to this box, right? definitely it is taking the signal from this box. That's the problem. Similarly here, right? And this box is taking signal from this one. This box is taking signal from this one. That means this box calculation cannot be done without this full adder sum, right? That's why. So this box depends here. 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 Correct? Yes or no? That's why the maximum delay what I could see is here. You see, signal has to start here. First of all, this computation of this box should be done. Then we can do this one. Then we can do this one. Then only 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 we can do this one. So finally, this is the longest path in this entire circuit. You see, you take any path, this is the longest path, and this calculation is depending on that longest path. I will explain very clearly, don't worry. See, 1 2 3 4 5 6, this is what the path, and we need this path because we can't escape that path. Why? Try to escape. Sir, I do one thing, sir. I take this path 1 2 3 4 5. Correct. After 5 delay, some of the signal is reaching here. What is that signal? This full adders carry. But we also need this carry. Correct. That means we should wait for this box. Fine. So I can say like this. We have to wait for this box for sure. Now, but this box is waiting on this box. That's why we have to definitely wait on this box. Okay. Now what I want to say is this box is waiting on this one. Correct. This box is waiting on this one. Sure, of course this box is waiting on this one also, but on this one also. You can take anything. For me same. Now this box is waiting on this one. Correct. Because now let me stop and just ask some cross question. Why this box is depending on this one? Because this full adder sum should be taken here, and after that we have to add here, right? So that's why this box depends on this box depends on this box. So that's why maximum delay path is definitely this one. 1 2 3 4 5 6. Correct. Now let's imagine you have n by n matrix. Sorry, not n by n matrix. You have n by n multiplication to n bit numbers. Then what I want to tell you is here in every level, see 1 2 3 4 5 6. Then how to imagine this for n bit I will tell you. Let me erase this part and I'll explain what is the delay because of n bit multiplication. Okay, see in this picture, so I am taking 5 bit numbers. Okay, 5 bit number multiplication, then you get this kind of grid. Correct. So first signal starts here 1 first of all signal should go through first block, then second block, right? So when you go to when the signal goes through 2 blocks, we will come here. Now again 1 block, second block. After 2 more blocks, we will come to next level. Try to understand. Initially we have 1 2 3, see level 1, level 2, level 3, level 4, level 5. My target is I want to come to level 5 first, because see this is the ultimate delay. 1 2 3 4 5 6 7 8 9 10 11 12, right? 12 boxes we have to cross, right? That many delays. Each box has some gate delays, right? So that's why for easy understanding we are assuming that one box has some C delay. Correct. So how many such C delays we will see? First we will be in the first level. After 2 block crossings, then we will come to second level. After 1 2, after 2 block crossings we will come to third level. So far we crossed 4 boxes. You can check it out. 1 2 3 4. Then now one more level, right? To come to one more level, 2 more boxes. One more level, 2 more boxes. So in that way, then we'll reach this point. Then after that, once you are here, 1 2 3 4. 4 boxes we have to cross. Then that 4 represents 5 minus 1. Correct. So now let's generalize it. So here after this 2 plus 2 plus 2 plus 2 plus 1 more 4, which is nothing but 5 minus 1, right? Then let's extend this to n levels, because when you are multiplying n bit numbers, we will be having n levels, right? 1 2 3 4 5. We will be in first level. To come to second level, 2. To come to next level, 2. Next level, 2, in that way. See, 1 2. 1 level, 1 2. In that way, how many 2s we are taking? 4. What is significance of 4 again? Because when you are in first level, to come to fifth level, only 4 levels to be crossed. Each time 2 boxes you are crossing, then 2 into that 4 is nothing but n minus 1 levels. Plus, once you come here, 1, 2, 3, 4, again one more n minus 1, right? So I can say that 3 into n minus 1 boxes we have to cross. Each box has some delay, so that is C. This is rough calculation, okay, one more or less. I am not exactly calculating, but approximately it is 3 into n minus 1. So I can say that around 3 into n delay, right? 3n. Now the space, if you see, you need huge space. Why? N by n, right? Every row should have n boxes. N into n square. N square boxes you want. Each box has full adder and AND gate, right? So if you are multiplying 32-bit numbers, then 1024 AND gates, 1024 full adders you require, right? Did you remember for addition how much you took? Okay. Did you remember? So around some 10, I mean for 32-bit numbers, did you remember? Let's do 4-bit, then you will understand. Let's take ripple carry adder. In the ripple carry adder, see full adder here, full adder, full adder, full adder, 4 full adders. For 32-bit, maybe 32 full adders, not more than that, correct? But here, n square adders we are taking. So n square blocks or n square boxes we are taking. That is a complexity of space, right? So finally what I want to say is array multiplier is very fast. Okay, slowly you will understand why it is very fast, because it took only 3n box delay, right? 3n box delays. So after some time you realize it will be definitely better thing, because you don't know other algorithms, right? I am going to teach you other algorithms. At that time we will see the calculation again, how much time they are taking. But here there are only 3n delays. It is generally very fast, but at the cost of space. You will be wasting lot of space, okay, lot of circuitry. Remember one thing in computer organization from now onwards, always there will be a trade-off. You can't achieve fasterness without sacrificing your space most of the times, okay. Remember this principle. Without wasting your space, you can't achieve speed in computer organization. Always there will be a trade-off between memory and speed. When you use lot of memory, you can, otherwise memory means here circuits. When you use lot of space, then you are going to achieve fastness, okay. But if you use very less circuits, then sometimes definitely speed will be reduced. Always that will be the trade-off. Just remember it. Just it's observation. It's not a theory. I can't mathematically prove it. But so many times we will be understanding that slowly by different problems. While solving different problems, you understand it. Today you have seen array multiplier, correct? So lot of circuitry, but fast. Now after this one, I am going to teach you sequential multiplier, after that booth multiplier, okay?